The next thing I want to talk about, which I'm a little bit excited about because it's just so much simpler than all the other stuff, and all the details I didn't talk about with Q-learning, how hard it is to get to work actually, all the small things you have to all the knobs you have to turn in order to make it work, and all the computer power you need to use. All this stuff I didn't talk about, so it's really hard. It takes a lot of craftsmanship to learn, and here's maybe a new approach, a new old approach, evolutionary strategies, that actually might make life a little bit easier for us. But of course it has hyperparameters like everything else. Here's the paper where they kind of rediscovered this approach from OpenAI, and there's also a link to the actual paper, and also a nice blog post about what they did in the paper. So the idea now is that, and this is illustrated in this 2D example, that if we have some objective function illustrated here, so we want to move towards the kind of heavy red areas, and we have a lot of computing power, so we can evaluate this function that we don't know, like this 2D function that we don't know, in a lot of places. Then we can have this kind of swarm of different candidate solutions, and we can evaluate the cumulative reward or whatever we want to optimize in all these points, and then we can move in the direction, in a clever way, move in the direction where we maximize our reward. So the idea now is that we have a set of parameters, we call them theta here, and we have a return or a cumulative reward f of theta, and now we want to evaluate our return in a lot of new places. So we start from theta and then we add some noise. So epsilon here is just IID Gaussian noise, and then we scale it with this hyperparameter, the standard deviation, how much we change in each direction. And then we update in the direction that will make f larger, and this is what I'm going to talk about next. But you can see the concept is very simple here, and you can see the nice thing about this is that we don't have to evaluate gradients, right? We are gradient experts in deep learning, but here we actually forget about evaluating gradients. It might also be that the return, the objective function, the cumulative reward we have, is not differentiable, then we cannot evaluate gradients. So this is a way to actually avoid that. So here's the algorithm. So you can see it's more or less what I talked about already. We have t is the number of time steps, and we have to choose like alpha, the learning rate, and then this kind of how much we perturb the parameters theta, and then initial parameter theta 0. And then we go over time, and we realize some random Gaussian noise, we add that to the parameters, and we evaluate the function, and then you can see in line 5 we update the parameters to the new point, as illustrated here. And the next slide I will actually show how we derive this expression. Because the expression is that we weight by the function evaluated in the new point, and then we move in the direction of the new parameters of theta, right? That's the difference between the old, or theta times sigma is the direction, is like the move from that version of that dot down here, and then we weight it with n. So I'll derive how we get to that, and that's actually something we have seen, something very similar before when we talked about the policy gradient. Because the idea now is that we say, okay, we want to calculate something like the gradient, but we have this f function which might not be differentiable, so we can make it differentiable by actually smoothing the function. So we do that here by saying that we now average our function over a normal distribution where the mean value is the current value of the parameters, and then we have this variance here, which is just an IID Gaussian with variance sigma squared. And now we can say, if we want to take the derivative of this function with respect to the mean value of this normal distribution, then we can use this result we had from policy gradient that we can write, or this reinforced algorithm, that we can write this as yet another average over our Gaussian smoothing here, and then we take the function f, and then we multiply that by the gradient of the log of the normal distribution. So if we calculate the gradient of a log normal distribution, we arrive at this expression down here. And you recognize here that this would be mean value. Here should be an expectation. We replace the expectation with n samples, and then we calculate this. You can see we have to calculate the here this is bad. I can see this is bad writing. There should be a sigma here. So we evaluate the function in theta plus sigma epsilon, and then we multiply here by the step size. Oh, sorry, this is coming from this derivative log normal, this quantity here. And then if we now go back and look here, you can see this is almost the same expression as here. The reason why we have here a sigma instead of a sigma squared. So let me see if I can say where that comes from. Why I cannot say that right now. Yeah, I had it on Friday when I had to write this. Okay, I'll come back to that. Or you have to look in the paper. But this, you can see, at least we are getting here to this kind of expression here. Yeah, there should be another theta. That's just probably the delta you get from the derivative. Yes. Anyway, so this is just to show you that this is how you get the smooth version and the gradient of the smooth version. So is this an efficient algorithm? Because this is a lot like that we actually try to evaluate a gradient of a function by taking by using random perturbations, right? And the next thing here, I will talk a little bit about whether this is a good idea, and it's a really kind of hand-wavy argument. But if we go one step back and think about the policy gradient. In the policy gradient, the way we make that differentiable is that we make our actions stochastic instead of deterministic. So that means in every time we make a step, for example, if it's a discrete action space, we draw from the softmax probabilities that we get from P of A given S. And that means that it's kind of random what actions we take. And that means that actually, if you think about calculating the gradient, then kind of this noise adds up. So if we take steps in a simulation, then the variance we get, kind of the noisy contribution to the gradient by using a Monte Carlo estimator, will grow with the length of the sequence. But if you think about about evolutionary strategies, we can use any action rule we want, right? We can have an argmax instead, and that means that our variance will not grow with the length of the sequence. So that means that if we have problems where, for example, let's say a game like Go, where we only get a reward in the end, then this kind of approach where kind of the variance doesn't grow with the length of the game is actually kind of would work well for that, or other games where we only get a reward very rarely. So that's a good thing. So the downside is that this way of evaluating the gradient essentially can be thought about as a finite, like a stochastic, because we draw this epsilon, a stochastic finite difference gradient estimation. And we know that these kind of finite different gradient estimations are really inefficient, because in a way we actually have to, if you think about the naive way, we have to evaluate the gradient, the one component at a time. So that means that if we have 1 million directions, we have to evaluate the function 1 million times, right? And this is more or less kind of how it would scale here. So in practice, these people from OpenAI, they are clever people and they have a lot of computer resources, so they actually ran this on a large CPU cluster, and they showed that this works almost as well as DeepMind's Atari approach with deep Q learning. They had to use something like 3 to 10 times as much computer power to get to the same performance, but you can say that it might be that this is simpler, so all the time that you spend in tuning and so on is saved. Might not be. There could be that actually this step size, for example, in perturbation of the current weights, that's really important, and they also mentioned some other tricks in the paper. But all in all, I think this is an exciting and new way to do things, because it shows that maybe a lot of the sophistication that we usually associate with reinforcement learning, you don't need to use that. You can actually use a very simple method. And again, it's an old method that has been resurrected in this computer age. And remember, computers are becoming faster and faster, so it means that more of these things that look stupid and naive will actually work when we scale them up to big computers. So that was all I wanted to say for this time. Thank you.